Okay, so welcome back to another video. So here today we want to show that the following inequality, so h sub n plus ln of h sub n is greater than or equal to ln of 2n. So I actually think this is a really cool inequality that we want to prove because for one, it's dealing with harmonic numbers. The nth harmonic number basically is just the sum of the some of the reciprocals at the n natural numbers. And of course dealing with natural log functions as well, so that actually puts a little twist on over here. So we start specifically the way to prove this following inequality is we want to start with a smaller result, namely a lemma in particular. Using that lemma to actually work our way up to prove the bigger picture, which is this inequality, in this sense the theorem. So this is actually interesting from using the lemma, but as we work our way, continuing on with the proof to achieve what we want, you're going to see some sums and integrals, and using those will actually help maintain the bigger picture on how we want to observe things, especially since we're actually dealing with inequalities. So you have to see what's bigger, what's smaller, and yeah, just utilize that, and basically that's just how we're just going to work our way up from there. So let's actually just jump right in. So the lemma we want to start with, so what we want to show for the smaller result in order for this to work our way up to get to the bigger proof of the theorem we want to satisfy, the inequality in particular, the lemma is going to be that the nth harmonic number h sub n is actually going to be greater than or equal to 2n divided by n plus 1. So how do we actually start this proof off? Well, if you actually know this inequality theorem, rather in a sense, this is known as the HMAM inequality. In other words, the harmonic mean and the arithmetic mean. And so when we say this, so by the HM, there's also including with the geometric mean and the quadratic mean, but with those four combined together in the inequality, it just says one is bigger than the other. Specifically, I think it's 0 is less than the harmonic mean, which is less than or equal to the geometric mean, which is less than equal to the arithmetic mean, which is less than or equal to the quadratic mean. But here in this sense, we can actually just focus on just the harmonic and the arithmetic mean. So by the HMAM inequality, we'll just lower this, we can say that this is the following result by saying this is n and then divided by 1 over 1, add this with 1 over 2, all the way up to 1 over n, and we can actually say that that's actually less than or equal to 1 plus 2 plus dot 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 plus n, all the way up to the n term, divided by n, right? So we know that as definition of a harmonic number, the nth harmonic number is just the sums of the harmonic series of the that partial. It's dealing with the partial sum specifically. So I can actually denote the denominator over here as n over h sub n, and this is still less than or equal to. So we know that 1 plus 2 plus all the way up to n is actually the partial sum of the nth of n natural numbers, but we know there's a closed formula for that, which is actually just simply n times n plus 1 divided by 2. So I'll put this back down here, then this just 2n. So now what I want to do is let's actually flip the reciprocal. So what that entails is that we also have to flip our signs of the inequality as well. So h sub n divided by n, which is going to be greater than or equal to 2n divided by n times n plus 1. So now we know that the n's cancel from both the top and bottom. And so n, so greater than or equal to, then we just have 2 divided by n plus 1. Then all we have to do is just multiply n to both sides, and so we have proven the lemma that we want to show. So h sub n is greater than or equal to 2n divided by n plus 1. And so just like that, we are done with the lemma. And so moving on from there, that means we can actually move on to the bigger proof, which now this will help us lead to the inequality we want to satisfy, which is the following h sub n plus ln of h sub n greater than or equal to the natural log of 2n. Okay, so from there, now I'll say, now we'll move on to the, moving on here. Let me actually now switch to another marker. Now I would say that by the lemma, so by the lemma, h sub n is greater than or equal to 2n divided by n plus 1. So now what we can do here is now let's actually take the natural log of both sides. So we have the natural log of the nth harmonic number greater than or equal to the natural log of 2n divided by n plus 1, which this is actually the same thing if we write this in terms of using our properties of natural logs. It's just ln of 2n subtract with ln of n plus 1. So now let's actually just add the ln of n plus 1 to both sides. So ln of n plus 1, then this is add this with ln of h sub n. This is still going to be greater than or equal to ln of 2n. So far we're kind of getting close. See, we have the ln of h sub n over here, greater than or equal to ln of 2n, but that just leaves us with what we're supposed to do with ln of n plus 1 in order to get from here to the nth harmonic number, which this is actually, this is where the fun part comes in. So here we're gonna actually make some observations here. So we're gonna start small and then work our way up to actually rewrite that, just to rewrite that ln of n plus 1, how we make the justification to move to the nth harmonic number. Okay, so now let's actually do that. So now notice that the observation we make is that if for some variable t, if we're in our closed interval from k to k plus 1, of course k being, you know, natural numbers, then you'll notice that, so then if we take the reciprocal specifically of t, so 1 over t, obviously you can see that this is actually going to be less than or equal to 1 over k. If it falls between that interval, then that means t has to be greater than k, or it can be equal, but that would have to mean that with the smaller number of the denominator is going to be bigger than the other one. So here we have this justification. So from there, now how about we actually take the integral of both sides with our bound from k to k plus 1. So now this will be 1 over t dt less than or equal to the integral from k plus 1 to k, or opposite, k to k plus 1 of 1 over k, and we're integrating this in respect to t. So if we actually integrate this, obviously 1 over t, its antiderivative is ln of t, then you just plug in your bound, so that would be ln of k plus 1 subtract with ln of k. Okay, so we still maintain the inequality over here. Now 1 over k is just a constant, there's nothing for t, so it's not dependent, so it's a constant. So then the antiderivative of that is just t divided by k. Put in your bound, so you have k plus 1 over k subtract k divided by k. If you just combine the denominators, then the k's will cancel, so you're actually just left with just 1 over k. Why don't we actually take the nth partial sum of both sides? So let's see, we have, our index is going to start from k, of course. K is equal to 1 to n of ln of k plus 1 subtract ln of k. Now we take the partial sum to the other side, so n, then k is equal to 1 of 1 over k. Okay, now obviously this right-hand side, by definition, this is actually just the nth harmonic number, so I can just replace that. But notice that this sum over here with ln of k plus 1 minus ln of k, if you actually do the series expansion, you'll notice that the terms are going to cancel out. So if I put 1, for example, so ln of 2 minus ln of 1, ln of 1 is just 0, of course. We go to 2, so ln of 3 minus ln of 2. You notice that the ln of 2 terms are cancel. You keep doing this so on and so forth all the way up to n. So really, telescoping series, you're just left with the first and the last term of the expansion, but obviously the first term is ln of 1, which is just 0. And so really, we're only left with just ln of n plus 1. So let me just say that this is telescoping. And so therefore we can make the justification and say that indeed, this is actually going to be just ln of n plus 1, which is less than or equal to h sub n. But with this inequality over here, we can actually do the substitution and just replace the ln of n plus 1 with h sub n, since it falls under that inequality. So it's still bigger than the others, so which is okay. So now going from here, we can now do the substitution. So now we have h sub n plus ln of h sub n, which is greater than or equal to ln of 2n. And so there we have it. We actually just proved our inequality that we want to show. So therefore, we're actually done. I wouldn't say therefore a second time because we just finished. So there we have it. proven using from the lemma by using HM and AM inequality, using that lemma to work our way up, and actually just used observation, which was by going backwards with the integral from k to k+1, work our way with using partial sums of both sides, then it leads to the inequality to the substitution that we want to put in to get our following. So yeah, that's pretty cool if you ask me.